Welcome to EE252 Electronic Devices and Circuits course. Today we are going to talk about BJT amplifier configurations. So far, when we looked at amplifier circuits, we always looked at uh, the BJT circuit connected in just one configuration. In other words, we always used the BJT. The input was always the base, output was always the collector, right? So when you gave the signal into the circuit, we used the signal between emitter and the base, and the output was taken from the collector with respect to emitter. So for both input and output, the common terminal was the emitter. So basically the emitter was grounded. So we were looking at circuits where emitter was grounded. Um, Even when you had emitter resistor, when you have a emitter bypass capacitor at signal frequencies, the capacitor works as a short circuit. So therefore, even under such situations, you could consider emitter to be grounded in small signal circuits, right? At higher frequencies, the signal frequency emitter was basically grounded in the AC equivalent circuit. And there was this one example that we discussed, in which case there was one resistor RE1 which was actually not bypassed by a capacitor. Under such conditions, even this resistance was small, and typically we consider even that as um, as a case of a common emitter circuit, right? So, however, this is not the only way we can input and output signals to a BJT amplifier circuit. So, since there are three terminals, base, collector, and emitter, you can choose any two as input and output, which causes the other terminal, which can be used as the common terminal. So in the circuits that we have seen so far, the common terminal has been the emitter, input has been given from the base, output has been taken from the collector. Likewise, if you want to choose another terminal, say for example, if you want to choose if you want to use the collector as the common terminal, you can input the signal to base and take the output from emitter, so which we call the common collector configuration. And in the case where you use the base as the common terminal, where you input the signal uh, from emitter and take the signal out from the collector, in which case we call this common base circuit, right? So likewise, we can have three different configurations. Now, one thing you need to remember though is sometimes you might think, why not we give the input from the collector and take the output from base while keeping the emitter the common? So aren't there six different configurations? Actually, the thing to remember here is that this is an amplifier. The purpose of an amplifier is to amplify the signal, not attenuate. So in order to increase the signal power, power for a resistive circuit is voltage times current. So in the case of an amplifier, the output power, which is the output current times output voltage, should be greater than input power, input uh, voltage times input current. So for the common emitter amplifier that we looked at, input power was base voltage or base to emitter voltage VBE times IB, whereas the output voltage was collector to emitter voltage VCE times IC, collector current, the output current. So this output power should be greater than input power. So this is why only one of those two possibilities are always used as the amplifier configuration. I hope this is clear. All right, so let's have a look at different amplifier configurations. We have BJT configurations. One, we have common emitter. Circuits. Number two, common collector. Three, common base. Right? We call this common emitter CE, common collector CC, and common base CB. A shorthand notation. Right. Let's look at the first case, common emitter amplifiers. So in which case, if you take the BJT, you have the base, collector, and emitter. You take the output from collector, input from base with respect to emitter. Okay, so this is the input, this is the output, and this is the common terminal. That is why we call it a common emitter circuit. Right? So some of the features about common emitter circuits are, now we looked at a general amplifier in the previous lecture. We said an amplifier can be represented as a voltage amplifier, current amplifier, transconductance or transresistance amplifier. In each of these cases, only three important parameters are there to characterize an amplifier. So if you use such a model to represent a BJT, we can look at what happens. So what are some general features about amplifiers in each of these amplifier configurations, BJT configurations. Okay. So, when it comes to common emitter amplifiers, input impedance of common emitter amplifiers is actually uh, not very low, not very high, but moderate. So in the range of about 1 kilo ohm. So we could say moderate to high. It's about 1 kilo ohms, which is not really high, but moderate. So we can call moderate or high input impedance. So this is in the range of 1 kilo ohms. The other feature is it has a moderate output impedance. When we say moderate, we mean in the range of about 50 kilo ohms. And its voltage gain is actually very high voltage gain. So this is R out, this is R in. So AV in the range of 100. Typically, the voltage gain, if you implement it in a circuit, common emitter circuit, this value is rather high, and also very high current gain. So AI also in the range of, this is not exact depending on different so let me say instead of E roughly equal, it's in the order of, okay, it's in the order of 50. This directly related to beta. Okay, so this is basically these are the features of a common emitter amplifier. Now if you look at an example we have seen already, so let's look at an example circuit. So this is exactly what, similar to what we have seen. So you have something like that. Let's put a emitter also emitter resistance also with a bypass capacitor. Okay, okay, so this is basically what it looks like. This is plus VCC, RC, RE. This is a capacitor bypass. Let's call it CE, R1 and R2, and you can feed the signal input through a capacitor C in, and look at the output at the collector connected through an output capacitor. Okay, so this is a typical uh, common emitter amplifier, BJT amplifier. Now, the when it comes to the gain of this, okay, so voltage gain, so AV of this circuit, roughly this value is equal to the resistance in the collector circuit divided by resistor in the emitter circuit. Now you can see that now what we are really interested about is not the DC potentials, it's about the AC potentials. So during the AC conditions, the capacitor CE looks like a short circuit, so therefore there is no emitter resistance. So will my output voltage gain be RC divided by 0, which is infinity? Actually, it is not. The reason for that is because though in the transistor we draw it like a diode in the base emitter junction, what you have there is there's a resistance to it also. It is not an ideal diode. So therefore, this resistance that you have, which we call dynamic emitter resistance, RE, is there. Typically, it is in the range of maybe 50 or 100 ohms, typically, which is considered a very small value, right? So therefore, it's called emitter spread resistance or dynamic emitter resistance. This is also inside this. So therefore, we need to add that also into this expression. Now, this emitter resistance, typically, if this emitter resistance is in the range of, let's say, 1 kilo ohms, but RE is in at the range of 50 ohms, then of course we can neglect this RE and assume there's only the external resistor that we have connected. But if RE is small, let's say 100 ohms, in which case the dynamic emitter resistance, simple RE, cannot be neglected. You need to add that also. Especially if you bypass the RE with a capacitor, then in that case, the only value that you have in the denominator is the simple RE or the emitter resistance. Okay, so therefore, this is basically what you have as the gain of the circuit. So when you have a capacitance, you need to remember that if there is this is when there is no CE, right? So this is equal to RC over RE. So, sorry, simple RE. When there is the emitter bypass capacity, right? Now, one thing to remember though is that we looked at this circuit earlier also. As the input increases, okay, as the input, so the signal increases, output actually just like that. Okay, so if you look at the output from the through the capacitor, then it would look something like this. Okay, so therefore this is basically inverted. So the voltage gain is actually negative, right? Voltage gain is negative. So you need to remember that this voltage gain is negative, negative voltage gain. Okay, some notes. Output is inverted, and this is the most common configuration for many applications. The reason for that is this has both a current gain and a voltage gain, which are greater than zero. So both high voltage gain and high current gain, which combine together very high power gain. That is P out divided by P in is very high. Okay, you can see if you have AV and AI 150, power gain may be like 5,000, right? Pretty big, roughly. If you don't have, if you assume ideal conditions, typically it is a little bit lesser. Okay, less than that. Okay, so these are some of the applications. This is an example of this. Okay, so so this is a very high, very high power gain. So this is why it is used in many applications. Okay, so this is our first amplifier configuration. The second amplifier configuration that I'm going to talk about is common collector amplifier, right? Number two is common collector amplifier. Common collector CC. Now in this case, my input is base, input is base, output is emitter. Okay, so this is my output, this is my input. Now with respect to collector, so this is my input, this is my output, right? So this is the common terminal. Common terminal is the collector, right? So some of the features about this. A common collector circuit, uh, it has a very high input impedance, very high input impedance, are in the range of about 100K, rather high, and very low output impedance, output resistance or output impedance in the range of 100 ohms. Okay, its voltage gain though is very low. Actually, it is very close to 1. low, close to unity, actually less than unity, almost unity, like unity voltage gain, like AV is about 0.99. So it's never more than or equal to 1, it's always less than 1, but close to 1. And now we know that a voltage gain is less than 1 to have a power gain greater than 1. So therefore, we have to have high current gain. Typically, so AI in the range of 50. This is like the beta. Okay, so it is similar to that. So if I look at an example, circuit would look something like very similar to the previous circuit, but you don't have a emitter collector resistor. You have resistance in the emitter, the biasing circuit, and you can provide the input through a capacitor, and there is no bypass capacitor across the emitter. So emitter is the load, emitter resistance is the load, and you take the output from the emitter. Okay, so this is the base, emitter, and collector. So the output is taken from the emitter, right? Now let me ask you a question. Now in this case, input is given at the base, okay, right here, the base, and my output is taken from my emitter. Now you know, for a BJT, this base emitter voltage VBE, so this is both AC and DC, is in the range of 0.7 volts DC plus a very small change in voltage as the input changes. Typically, it may change from maybe 0.69 to 0.71 or maybe 0.65 to 0.75, very small, less than 10 millivolts fluctuation around 0.7 plus or minus plus or minus 5 millivolts will be there as the input is applied. So output typically is almost the same voltage. As you can see, the voltage gain is this, so it's 1, roughly equal to 1, right? So there is no voltage gain, the same input goes to output. So why would anyone use this circuit? Because you are not gaining any voltage here. Why would anyone want to use it? It's a bit of a tricky question, because the reason why it is used is because of its other properties. Yes, it is not giving any voltage gain, but it gives a current gain, right? So input current may be very small, but the output current can be very large. And you can look at it in a little different way, right? If you look at the features about this, you see that it has a very high input impedance and a low output impedance. So let's say I have a microphone. Okay, output voltage of the microphone could be very output of the microphone uh, cannot deliver a large power. Okay, so the current can be very small. The output power of the microphone can be small. So therefore, if you directly connect it to a high load, it is not, the microphone is not going to be able to deliver the required power. So therefore, you are not going to hear anything out of the speaker, which may have a low resistance. High load means low resistance in the range of maybe 100 ohms, maybe 10 ohms, maybe even smaller, depending on what you have. So therefore, it cannot deliver that current. So if you use this kind of a circuit, a common collector, voltage you can keep as it is without changing, but output impedance of this circuit is small. So for a uh, microphone, output impedance will be very large. So therefore, um, it could be in the range of tens of kilo ohms, or maybe even more, maybe uh, hundreds of kilo ohms. So therefore, if I directly connect a 100 ohms speaker, this is not going to deliver much voltage to that microphone to speaker at all. So therefore, instead of that, if I keep the if I pass it through a buffer circuit, or if I pass it through a common collector circuit, which is sometimes called a buffer circuit also, we'll see why it is called a buffer circuit in a minute, then it can actually provide, its output impedance is pretty small, like in the range of 100 ohms. So therefore, it can drive a much bigger load. You can look at it in a different way. You can look at it as you do, so because the input impedance of this circuit is high, so you can look at it like this. So, so it's, there's a current gain, but not a, so very high R in and R out uh, is small. So therefore, um, you can drive a load without actually uh, loading the source. So the input current that it draws is very small. I in is very small, whereas I out can be large. Okay, so this is why this is used. Sometimes this is called a buffer, because in computer applications there are a lot of applications where the digital lines are, they cannot provide the uh, they cannot provide the current, but they just maintain the voltage. So if you want to use a signal from it to control something, you need to send it to a buffer, which can provide the current capability. So that is why it is called a buffer. So this is often used as a buffer circuit or a voltage follower. We sometimes call this a voltage follower also, which means the voltage is the same, it doesn't change. Okay, most often used as a buffer. In other words, drive a low impedance or high load using a high impedance source. So this is the mm, main application of a common emitter amplifier. It's actually very highly useful circuit. Okay, so we have talked about two types. The last type that we are going to talk about is the common base type. Common base amplifiers. Obviously, uh, here you have the base emitter and the collector. You your input is actually between base and emitter, whereas your output is actually between, this is the input, is the output. This is the common. Okay, so this is basically what you have there. And the features, one, this is the opposite of what you saw earlier, the common collector, where you have low input impedance are in the range of 20 ohms to high or moderate to high output impedance are out in the range of mega ohms, 2 mega ohms, 3 high voltage gain AV in the range of 100, but low current gain AI in the range of 0.98. So low current gain. So this is unity, close to unity. Okay, so this is the previous buffer circuit, or the voltage follower had unity unity voltage gain. So we called it a voltage follower or voltage buffer. This is a unity current gain. So we call this a we call this a current buffer. This is also called a current buffer. Okay, this is a current buffer which keeps the current constant while amplifying the voltage. So you see now voltage gain is high, current gain is almost 1. So therefore you have a power gain. Okay, AV times AI is much bigger than 1. Okay, so the power gain is still there. Now these kind of things are the least used in our applications in this course, but these are used mostly in RF applications, RF amplifiers, radio frequency. RF amplifiers are, so we use this in RF amplifiers. So this now we are going to look at some uh, models of the transistor later on, and you see that at high frequencies there is some parasitic capacitance between each of these terminals, base, collector, and emitter. So sometimes the effect of the parasitic capacitance between base and collector, due to that there will be a leakage current between the base and the base and the collector, and the effect of this is the reduction of the bandwidth. At high frequencies there's a leakage, so therefore there's a reduced bandwidth. So to avoid this, we use this kind of an arrangement, and is called is therefore these are used for high frequency applications. Okay, reduces the effect of base to collector capacitance in reducing the bandwidth. Bandwidth is the range of frequencies that are passed, that are amplified. So therefore, to increase bandwidth, so this is called BW, to increase BW bandwidth, use this in high frequency applications. we use common base amplifiers, and also in some regulated power supplies also. Now, typically, uh, because this doesn't give you any voltage gain, we have a common emitter amplifier before this also. Okay, so typically fed through a common emitter amplifier, because the input impedance of this is pretty small. Uh, Often the source can be overloaded if you directly connect this. So to avoid that, we use a common emitter amplifier to obtain both the voltage gain, both the current gain as well as the uh, input impedance requirements. Okay. Okay, let's look at an example here. Example circuit of common base circuit. Um, let's minus VEE plus VCC RC RE. So this is your DC circuit, and you send the input through the emitter like that, and output taken from the collector. All right. So this is your V out, this is your V in. So this is an example circuit of common base amplifier. Okay. So this is typically what you have. So these are the three different configurations that we are going to talk about, and um, we can summarize the properties of these here. So let me tabulate this as a summary. So the quantity, like the current gain, voltage gain, input impedance, and output impedance for the common emitter, common collector, and common base amplifiers. So for common emitter, in both current gain and voltage gain are high. So this is in the range of 50, sorry, it's in the range of 50. This is in the range of minus 100. Okay, so it's inverting. Input impedance is medium, like 1K. R out is also medium, in the range of 50K. For the common collector, you have a high current gain, just like before, about 50, but unity or unity voltage gain is in the range of 0.99. Unity voltage gain. Input impedance is high, it's in the range of 100 kilo ohms, and output impedance is low, in the range of 100 ohms. On base, low current gain or the unity current gain, is about 0.98. High voltage gain, about 100. And low input impedance, about 20 ohms. And high output impedance in the range of 2 mega ohms, so very high. These are the features of different amplifier configurations. Okay, so this is basically this concludes our section on amplifier configurations. Thank you.